try. So what I would like to do is, so before getting to the fun part of actually computing things and using this whole theory, today we have to suffer a little bit with the definitions and see how the contact invariant is defined and why it is well defined, and check basic properties. So this is a little introduction to contact Oswald-Szabó invariance. And yesterday I already declared the basic properties, but now let me just start with the definition. So suppose that Yxi, as always, closed contact three-manifold is given. And as we just heard from in John's lectures, we can choose a compatible open book decomposition with connected binding. So suppose that B pi is a compatible open book and B is connected. So now we can perform a surgery along the binding. So let YB denote zero surgery along the binding, along B. So let me just pause for a second. You have to remember that whenever we talk about surgeries, the coefficients should be measured with respect to some framing. But now, luckily, the binding is homologically trivial, since the page is just a ciphered surface for it. So we just do zero surgery with respect to that framing, and we get a new manifold. Now the claim is, the first claim you have to see is that YB fibers over S1. So it's actually a surface fibration over the circle. And this is sort of not very hard to see. Away from the binding, the manifold already fibers over the circle because it's an open book. That's the very definition of it. But unfortunately in Y, the fibers, the pages just sort of come together like an open book. Right? So if this is B, then the fibers will look like this. Now, I'm not very good in drawing open books, but I hope you get the picture. And now we just take out B and glue it back in a way that what used to be the longitude now becomes the meridian, and what was the meridian before now becomes the longitude. So we just cap off all the fibers. So we have a fibered three-manifold. Okay, so that was a proof, if in case. So now here is a sort of a proposition which is important, and it's sort of interesting to note by itself that let T denote the spin C structures of YB, which have the following property: C1 of T evaluated on the fiber is just twice the genus of the fiber minus 2. So remember, these are those classes which still have a hope to have non-trivial Heegaard Floer invariants because of the adjunction. If this evaluation is any higher than this value, then the Heegaard Floer groups are trivial. And then the statement is that then HF hat of YB T is equal to HF hat of YB T can, which I will just define in a second, Z2 plus Z2 once G is high enough. It's at least 1. It's at least 2, higher than 1. Okay, so what is the moral? What's the message? First of all, we just take any this holds for any fibered three-manifold, and we take those spin C structures which evaluate extremely on the fiber. And then the The content of the theorem is that if we take all those spin-C structures and we compute the Heegaard Floer groups with respect to those spin-C structures, then in fact we get a constant answer. The answer will be always the same. This might seem to be sort of disappointing because it says that from the fibration we just don't get any kind of information, but you should regard this theorem as the counterpart of the fact that if you have a fibered knot, then the top coefficient in the Alexander polynomial is just 1, or the highest spin-C structure gives you a trivial z in the Heegaard Floer theory. So does the statement make sense? How do we prove such a statement? So I will just very quickly outline the proof. I switched the board, right? This is the... I didn't tell you what T canonical is. So whenever you have a fibration, it comes with a canonical two-plane field, the tangents of the fibers. And T canonical is induced by that. And it's not very hard to see that T canonical is actually in script T. So the meaning of this first line is that we might potentially have lots of spin-C structures in script T, but only one of them will actually contribute to the Heegaard Floer groups, and it contributes in a constant manner. Okay, so the proof consists of two steps. First, independence of monodromy. So you know, such a fibration YB can be described by two pieces of data. You tell me the typical fiber, so you just specify the genus, and you specify the monodromy. And in the first step, we would like to show that actually the answer, the Heegaard Floer group, will be independent of this monodromy. So how do you do that? So suppose, I will just outline what you have to do, and it will not be very hard. Suppose we have two fibrations with monodromies. What are the letters? Phi 1 and Phi 2. Then consider Phi 1 composed with Phi 2 inverse. This is just an element in the mapping class group of the typical fiber, and luckily it can be written as a product of TCI, where TCI, or D. That was some number of elements in the mapping class group, which are all right-handed Dane twists. This is sort of the same principle as John appealed to, except in his case, the fiber was a surface with boundary, so besides the Dane twists, there were Dane twists coming from the boundary. And also he chose left-handed Dane twists with stick to right. Okay, so now of course what we will do, we would like to prove that the two fibrations with monodromy Phi 1 and Phi 2 give you the same Heegaard Floer groups, and we will do it by induction on N. So suppose I, yeah. So you just write it down as a product of a couple of Dane twists, and you can assume that you only have one, and then you just keep doing. So suppose that Phi 1, Phi 2 inverse is actually a Dane twist. And then we just learned from John in the open book case, but somehow the whole argument was very local, that you have your fibration with Phi 1, so let's denote it like this. Y Phi 1 is the fibration with a fixed genus and monodromy Phi 2, and the way you get, Phi 2, and the way you get to Phi 1, which is just Phi 2, I got completely mixed up, right? Anyhow, is a surgery along the circle C, along which we take the Dane twist. He argued it in the page of an open book, but everything happened to be far away from the binding, and the same argument just passes through. So this is a -1 surgery along C. And we would like to argue that somehow this map induces an isomorphism on Heegaard Floer groups. If we can achieve that, then we are done. And the moral is, whenever you would like to get an information about the map, you just put it in a triangle. You know, it's a one-handle addition, so here is one fibration, the other one, and then what you have to do is you just consider y prime, where you get y prime doing 0 surgery on C. The surgery coefficient should be 1 higher. So this is -1 surgery on C, and this is 0 surgery on C, right? And now I claim that actually this term just contributes 0. And this implies that this map is an isomorphism from exactness. And this is sort of easy because you see what happens is this. Here is the typical fiber, and we just take a circle C. Sorry. So this is C. And when we go from here to there, we just do a -1 surgery along C. When we go from here to there, we do 0 surgery on C, 0 with respect to the fiber. So this fiber will look like in y prime like this. Not like this. Something like that. Right? It just, no, what happened? Like this. You just open it up. You just cut out a little neighborhood and you glue back with the disk. So what happens is you lose genus. So those spin C structures which evaluate maximally on in this case, will evaluate too much on that circle, on that surface. So by adjunction, the Heegaard Floer group here will be 0, so you get an isomorphism there. So this is how you get the independence of the monodromy, and then the next step is a model computation for every genus. Say you take 0 surgery on the torus knot 2G+1, you have to prove that this will become a fibered manifold with genus G fibers, and you have to compute the Heegaard Floer groups for that. Luckily, there is another triangle which connects S3, this one, and some high enough surgery coefficient. Peter just talked about this triangle. And we know that it is an L space if n is high enough. We know that this is an L space, so this will just help us to compute what the group is. So this shouldn't be, you shouldn't treat this as a proof. This is sort of a hint how to do it. So first you get rid of the dependence on the monodromy by one triangle, and the other triangle just gives you a typical a model computation for every genus. And this is how you verify that, in fact, this holds. Let me just mention another way of doing the same without giving too much of details. So, in fact, can do by drawing an explicit Heegaard diagram. And in the prescribed spin C structures, you will just see 2 intersection points. With 2 intersection points in T. In these spin C structures, you just have 2 intersection points. Of course, for this, you have to choose your base point wisely. So you're not really needing a Heegaard diagram, but you need a PhD for that, right? So that's a little harder. In fact, the two intersection points will be connected by a holomorphic disk, but the holomorphic disk will have NZ phi equal to 1. So it will not contribute to the HF hat computation, but it will contribute to the HF plus computation. And this argument also gives the following proposition prime. If Y be fibers, then HF plus YB in T is just Z2. Somehow the two intersection points will have zero boundary in HF hat because the holomorphic disk passes through the base point Z, but if you count HF plus, then this holomorphic disk comes alive and it will just cancel the two generators. But this makes us able to sort of distinguish a generator in HF hat. You have to remember that HF hat and HF plus are connected by a long exact sequence. And so you just take that generator from here, which maps to the generator there. So I should write that down. And then we are essentially done with the definition, and then I will indicate why is it independent of the choices we have made. So let age from HF hat of YB T be the generator which maps to HF plus, or to the generator of HF plus YBT. In the Heegaard diagram, in the pointed Heegaard diagram, somehow it can be seen that the holomorphic disk goes from one intersection point to the other, and you just take the first one from which the holomorphic disk starts. And this is the distinguished generator there. In any case, somehow, the moral is that if you have fiber three manifolds, in the highest possible Chern class, the Heegaard Floer group is very simple. It's just Z plus Z, and there is a good way to select one generator for this Z2. And this is what I call H. Notice that we are working with Z2 coefficients, and there is a very good reason for that. If we are working with Z coefficients, then this H is defined only up to sign. Right? So then I have to keep track of this throughout the lecture, but I don't want to do that. So, and notice also that it doesn't have to do anything with contact geometry or open books. This is just about fiber three manifolds. And so now we can get to the definition of the contact invariant. So take Y psi open contact three manifold, fix B pi open book with B connected. Consider the cobordism X given by zero surgery on B, and take, and now comes the definition, Cy psi to be equal to Fx bar H, which is supposed to be an element of HF hat of minus Y, and I think I explained everything except what do I mean by X hat. Where X bar is the cobordism X turned turned upside down. So let me just give you a schematic picture. So here is your Y. This is a 3-manifold. In order to attach a 4-dimensional 2 handle, you just thicken it a little bit. You just take Y cross 0, 1, and then you attach the 4-dimensional 2 handle. This corresponds to the 0 surgery on the binding, and you get YB up here. So you get a cobordism from Y to YB. But this is not what you would like to have. You would like to have something from YB to Y. So what you do is you just turn everything upside down. But then, of course, what was in before becomes out. So instead of going from YB to Y, you get something going from minus YB to minus Y. So this is minus YB, and, well, you know, this is sort of turned upside down, whatever it means. So this is the reason you will have your invariant in the Ožvat-Szabó group of minus Y instead of Y. Of course, if we go through the Seiberg-Witten story, then it is sort of natural to have a cohomology element as opposed to a homology, so this shouldn't be sort of unexpected. Okay, so this is the invariant, but the question is why it is an invariant. There was one choice we have made, namely we chose the open book. So we have to make sure that this is independent of the compatible open book. But we know from Giroux's theorem that what we have to check is that if we make a positive stabilization, then we still get the same invariant, the same element. But in fact, since we are stick to connecting bindings, we will always do 2 stabilizations. If you do one, then your binding will become disconnected, and then you do another one. And so we would like to make sure that the element doesn't depend on that operation. And so for a while, the proof proceeds nicely, and then it gets really wild. And so I would like to tell you the story until it is nice, as always. You know, you want to keep this image of talking about nice things all the time. Okay, so how is it going? So here is the proposition which we can prove. So for a while I will just change notation, and since we don't know whether it is really independent of the open book, I will denote the element coming from a fixed genus and fixed monodromy phi as the invariant. And then we would like to sort of show that it is independent of these 2 data. So here is the proposition. For every age, there is an element C phi age of minus Y, which has the following property, such that if phi prime is a genus age stabilization positive of phi, then C phi of age is the same as C phi prime. So what do I mean by this? So up till now, as the definition suggests, we are not having a contact invariant. What we have is an invariant of open books. And I would like to convince you about that, in fact, for positive stabilizations, you always get the same element. And the way we do it is, first we would like to get rid of the dependence of the actual monodromy of the stabilization, and then we would like to get rid of the dependence of the genus of the stabilization. Very much like in this previous proof. So this is the proposition I will prove, and then let me just run a little bit ahead. Then the next step would be show that C phi 1 is the same as C phi 2, and so on. And these are all the same as C phi, the element defined by the monodromy, by the open book you just picked. And of course, I mean, again, the magic of induction tells you that you only have to prove that this is equal to that, and the rest will just follow. So in fact, it boils down to C phi equals C phi 1. And then how do you do this? And the hope is something like you take, so how could you prove something like this? You just take your open book and you just pick whichever stabilization you want. Whichever positive zero stabilization you want, then you just have to relate the two things. The problem is that this is a genus G and this is a genus G plus 1 open book. And how do you relate them? And there is no good way to relate them. That's the bad news. So when I was talking to Peter about this proof, he said that until here they had it much earlier. Once they heard about this story of Giroux, they immediately worked out the invariant until here. But how do you prove this last bit? That's sort of hard. You have to relate genus G and genus G plus 1 fibrations. And you would like to find a cobordism and put it in a triangle, and they couldn't find it. So if you cannot do it directly, you do it indirectly. And what happened is that this is the point where they used the not invariants. So they identified these elements by the not invariant, the invariant given by the binding. And they made a computation. And here the binding is B. And if you wisely chose your stabilization, the binding will become B connected sum with the right-handed trefoil. And somehow connected sum goes into tensor product, and the trefoil is somehow the simplest example. It will become 1, and so this is how they prove this next step. I don't want to go into the messy details of this argument. I just would like to indicate how it goes. But so the story is that everything works nice and smooth in the 3- and 4-dimensional world up till now, and here you need the knots, the not invariants. So let me just give you a little idea how to prove the proposition up there. And the reason I want to sort of run through the proof of this statement is that because it shouldn't sound new. This will be sort of the combination of what we were doing until now, together with the ideas John was just telling you a few hours ago. Okay. So what do we do? So proof of proposition over there. Okay, so what do we do? Let's take the monodromy phi connected sum with the identity on the genus H surface. So remember, we have some typical fiber of our open book we chose on Y, and then there is a monodromy which just the identity near the boundary of sigma. And we just add, how should I draw it? I never drew this before. You just add a genus H surface to it. Maybe now I know how to do it. And then you just take like this, genus H, and you extend your phi as the identity there. Okay, so a little exercise tells you what the resulting 3-manifold is just Y connected sum with 2G copies of S1 cross S2. That's sort of a little exercise. So you have Y, you have this new 3-manifold, and then so how do we get from Y to this? You can get from Y to Y connected sum 2H S1 cross S2 by adding 2H 1-handles. So actually you get a cobordism from here to there, or if you turn everything upside down, or there is X cobordism from Y minus Y connected sum 2H X1 cross S2 to minus Y by adding 2H three handles. So until now, the proof is in a pretty bad shape. Somehow we even changed the three manifold, so we have to do something about it. And so now I just declare, what do I do? Okay, so define C phi H as Fx C phi connected sum with the identity. So remember, whenever we have an open book with a monodromy, we have an invariant. We would like to show that it's not actually an invariant of the open book, but the context structure. So we just take the invariant for that open book, and we map it into our original group. And we would like to show that no matter what kind of monodromies we took, if it is a genus H stabilization, then we always get the same value. Okay, and so the proof concludes with a lemma, which will be useful anyhow, which says the following. Which is what? Oh, I see. So, how do we get from a genus H stabilization to this? So what does a genus H stabilization mean? That we have our original surface, and then we just connect them. And then we have to give the new monodromy elements, alpha 1, alpha 2, along which we are supposed to do right-handed Dane twists. So the idea is just undo the Dane twists dictated by the Giroux, by the positive stabilization, and show that we get to the same element, to this fixed. Okay, so the last step is again an application of the exact triangle. Okay, so instead of elaborating more on this step, I just want to give you the big picture. So the idea is that you choose an open book. The open book gives you an element, and you would like to show that it is independent of stabilization. So first you sort of treat the monodromy, and you prove that it's independent of the monodromy, and then using the not invariants, you prove that it is independent of the genus as well. Okay. So let me just turn to the basic properties of Cy psi, of the contact-Auger-Szabó invariance. So the first theorem is this. So suppose L is a Legendrian knot. And this is the property I listed last time, is equal to +1 surgery along L. Then F minus X C Y psi is CYL psi L, where X is the cobordism given by the surgery, and minus X is equal to X with reverse orientation. Okay, so it just tells you how the contact invariant changes under +1 surgery. Remember that this is a linear map. And the magic is somehow that you have to flip the orientation here. Okay, so how does this proof go? So fix B pi open book for y psi such that L is on a page. John just explained it last time how to actually do that. So now let's consider, so here is y, and we just flip its orientation. So we have minus, okay. This is YL, and this is the cobordism X, induced by attaching a two-handle along L. So as John explained, what happens is that we will still have an open book here with the same binding, but we just add one left-handed Dane twist to its monodromy. The point is that everything sort of happens far away from the binding. So the two things will have the same binding. So let's take zero surgery along the binding. You get YB and YBL, right? And the same cobordism can be done here. You can just attach to these guys the same two-handle along L. So I call it XB. Okay, so now we just reverse the orientation of X and XB, and turn these cobordisms upside down. So we have minus YB minus XB minus YBL. So shall I give names to, let's call it W and WL. So this is W bar and WL bar, and this is minus Y, and this is minus YL. Okay, so we are almost done. So what's going on? Whenever you have a situation like that, this induces maps on the Heegaard Floer groups. And we are almost at the punchline. And remember, the very definition of CY psi is just you take a preferred generator here and you map using this cobordism down. So there is an age in here, and this is just FW bar of age, right? And we have age L here, which is mapped down to this group by FWL age L, and this is exactly CYL psi L. And we would like to argue that this F minus X just takes this element to this. And of course the the question is just what happens with H, whether H is mapped into HL. But that's sort of clear. This is what we actually already proved. This is how we proved that the two groups are the same. You just fit this into a triangle, and the third term will be just 0. So you just have an isomorphism here. Since F minus XB H is HL, we get the conclusion. So this is sort of a long story until you set it up. At the end is somehow easy, and you have to see that we insisted on doing +1 surgery because we wanted to have, in the reverse orientation, we wanted to have a -1 surgery. So when we hire the coefficient in the triangle, it becomes a 0 surgery, and for that we know the vanishing of the Heegaard Floer groups. So using, so there is this HF hat, and I called it, I don't know, Y prime. And we know that this vanishes for the particular spin C structures because it violates the adjunction inequality. It's always good to use colors because then it becomes completely indistinguishable in the notes. Okay, so we have this rule. So again, one attitude to the whole story is that there is some magic which associates to contact structures an invariant which transforms in this manner. Let's see what follows from that. So let me just give you some consequences. So I announced a theorem last time saying that these invariants are 0 for over-twisted structures, right? So here's a proposition. Y psi is over-twisted, then Cy psi should be 0. And the way we'll prove it, we'll appeal to Eliashberg's theorem, saying that over-twisted structures are in one-to-one correspondence between two plane fields. So here is how we do it. Consider this contact structure. It's not very hard to see that in fact this is an over-twisted contact structure. I will leave you as an exercise. You just take this circle and you should prove that this circle in fact bounds a disk in the surgered manifold, and then one has to compute the two framings coming from the disk and coming from the contact structure, and you could see that it's equal. I warn you, there is a very strong temptation to say that of course this circle bounds a disk, here is the disk. This disk is in S3 but not in that S3. You make this surgery, you turn this into another S3, and the surgery curve will just puncture this disk, so this will not be a disk anymore. But if you try a little harder, you will see that this Hopf band eventually, which is an annulus, can be closed up to be a disk in the surgered manifold. So, this is a very good exercise in training your mind how to work in surgery, in surgered manifold. So this is which is over-twisted. Okay, so now Y psi has a certain two-plane field, and this over-twisted contact structure is some other two-plane field. So it's not very hard to see that there is a two-plane field hence a contact structure psi prime on Y such that Y psi is isotopic to, well, homotopic to y psi bar connected sum, my favorite, the shark. Okay, you know, somehow this guy adds 1 to the framing invariant of the two-plane field, so you have to take psi bar, which is just 1 behind psi in the framing coefficient, and then you just take this connected sum. But whenever two over-twisted contact structures are homotopic, they are actually isotopic. So what we really have to compute is what this is. This is our original question. This is the same. But now it's sort of easy because, you see, the way you get to this connected sum, is to take a Darboux chart and do a +1 surgery along the Legendrian shark. So we can use our principle. So Cy psi is just the same as fx, f minus x, of Cy psi bar, where minus x is the cobordism, where x is the cobordism given by the two-handle attachment -1. See, the unknot, which has Thurston-Meneke number -2, and we do a +1 surgery, so it's -1. So far, so good? Sorta? Okay, so here we just used Eli-Ashberg's theorem, and now we will use our principle. You know, the first thought which can come to your mind is that this guy can be chosen to be over-twisted, so we just do induction, and this is 0, and this guy is just a linear image of 0, but then induction gets sort of difficult if we remember that the two-plane fields are sort of cyclically parametrized by the framing, so you just very quickly get back to where you started from. So that's not a good idea, but we can realize immediately that independently of what this element is, the map itself is 0. So now the proof concludes by observing that f minus x is in fact 0, since it contains a sphere of self-intersection +1. Right? X contains a sphere of self-intersection -1, the sphere coming from the spanning disk of this surgery curve plus the core of the two-handle. So when you flip the orientation, it will become a +1 sphere, and the adjunction formula just tells you that there can be no spin C structure for which this map is non-trivial. Whenever you are in trouble, you just call the adjunction formula. This is the really helpful thing which connects up all these really fancy defined invariants with the actual geometry of the 3 or 4 manifold you are working with. Okay. So that's good, but there is always this danger that after so much work, we define something which is always 0, and that's sort of less fun. But so next I would like to give you a couple of examples where the invariant is non-zero. But before doing that, let me just tell you another observation. Okay. Proposition. If L is a Legendrian knot in Y psi and Y upper L, psi upper L is given by -1 surgery, contact -1 surgery on L, and C of Y psi is non-zero, then C of YL psi L is also non-zero. So doing a -1 surgery cannot turn a non-zero element into 0. And the proof rests on the observation which already appeared once, saying that somehow a contact -1 surgery, the effect of a contact -1 surgery can be cancelled by a contact +1 surgery on its push-off. So by cancellation, YL psi L contains L prime such that +1 surgery on L prime gives Y psi. Somehow you should see that these +-1 surgeries correspond to Dehn twists with exponent -1 and +1, and so in the group level you clearly see the cancellation, and this is exactly what happens on the contact level. But then we are done, right? So this just says that that Cy psi is the image for some cobordism, for which we even have to inverse the orientation of YL psi L. Nevertheless, if you have a linear map which takes an element to a non-zero element, then this shouldn't be 0. So John mentioned the problem, saying that suppose you have a tight structure, tight contact structure, and you do a -1 surgery, whether the result is tight or it might be over-twisted. We know that if the structure itself is fillable, then it's hopeless. Then the -1 surgery will give you another fillable structure, so it will be tight again. Now you see that if you start with Y psi and it has non-zero invariant, then the result will have non-zero invariant, so you are not supposed to look among these examples as well. And at the moment, we don't know any tight structure which is neither fillable nor has non-zero invariant. So somehow our chances are sort of limited at the moment to disprove that statement. So it depends on your attitude. Then you say, okay, if you cannot prove the converse, then it should be true. But you have to keep in mind that we know very little examples. Somehow the examples we sort of understand come mostly from like Seifert fibered spaces. Okay. So again, one word about the moral, how these maps actually work. So when you do -1 surgery, then you expect to keep the tightness condition alive. When you do +1 surgery, you expect to ruin tightness somehow. And so the way the maps work is that you have something and you map it into the result of a +1 surgery. So whatever it was, this element has a higher chance to be 0 than this one, right? And the -1 surgery just goes in the other direction. If this was not 0, then this shouldn't be 0. So somehow -1 surgery is just the inverse, whatever it means. Okay, so another model computation. So example. What's the deal with this? The Legendrian unknot with +1 surgery. So we are not really, oh, I see. I forgot to tell you one more fundamental fact. Let me just use another word for that. CS3 with the standard contact structure is not 0. I will not prove that, but actually you can just sit down and do it from the open book decomposition John was giving you with the circle binding, with the unknot binding. To appreciate this fact, you should realize that this is an element of this group which happens to be equal to Z2. So in other words, this is the only non-trivial element in the Heegaard Floer homology group where it lives. If you wish, we can put a minus in front, but it doesn't really make a difference. So I don't want to prove this, but that's not very hard. And actually, the triangle I will give you in a moment would prove this statement as well. Okay, So example, this is not 0. So this just shows you that +1 surgery, although it has the tendency of ruining tightness, it doesn't always do that. So how do we prove this? So what's the rule? We have S3 with the standard contact structure, and we do a +1 surgery along the Legendrian unknot, which instead of the saucer, now it will become this funny looking hat, and you get here. A moment of thought shows that this is just a 0 framed unknot, so the 3 manifold is in fact S1 cross S2. Okay, so now how do we compute the invariants? We have to flip orientations everywhere on the 3 manifolds and on the 4 manifold. So we get, but it will not be apparent in this instant because minus S3 is the same as S3, and you just, this is not the same circle I reflected, and I also multiplied the framing with -1, but it just doesn't show. Yeah, you see? Okay, so this is a 4 manifold, this is a 3 manifold. Okay, we would like to see what this map does with this single generator. It can take it into 0 or non-zero, and I would like to just argue that in fact it is an injective map, giving that this is non-zero. Whenever you would like to analyze a map, what do? You just take it into a triangle. So what does the triangle say? You just take linking -1 there, and you get y prime, and here you just take, so I introduced this notation last time that I have to put the dot. You know, the circles are like this, right? Okay, and here, so this is the triangle on the manifold level, and then we turn it into Heegaard Floer groups. And so we get HF hat of S3 or minus S3 going to HF hat of S1 cross S2, HF hat, and we have to understand what this manifold is, but again, one single Rolson twist on this -1 will turn it into infinity, to turn it into 1, so this is S3 again. And here is this C as standard. And the question, where does it map to? We know that it maps to the invariant, but the question is whether it is 0 or not, the image of that element. But now we just compute the groups. This is Z2, this is Z2, this is Z2 plus Z2. So the only way this triangle can be exact is that this is 0, this is injection, and this is surjection. So luckily, we got that this contact structure is tight. That silence. Is it okay? Is that okay? As Zoltán used to say. Okay. Now, we have a classification of tight contact structures on S1 cross S2, and in fact, this is equal to the boundary of the Stein one handle. And so this argument just shows that it has non-trivial invariance. And John just mentioned the fact in the previous lecture that if you have a Stein manifold, then it can be given by Legendrian -1 surgery on a couple of Stein one handles. So just to disprove together with the transformation law what happens with -1 surgeries, you just easily get the corollary that if y psi is Stein fillable, then C y psi is non-zero. Now, before closing, let me just make remarks. In fact, if y psi is weakly fillable, then it's invariant. Well, we cannot state that it is already non-zero. There is a twisted version of the cohomology theory of this whole homological setup, which provides you a twisted version of the invariant or cohomology with local coefficients, which turns out to be non-zero. And this is actually the important piece of information used in the statement what Peter was talking about, that the contact homological argument sort of detects the genus of the knots. So this is actually the computation they need. Without the twisting, it doesn't hold, since Paolo Gigini found an example where the contact structure is weakly fillable but has untwisted mod 2 invariants being equal to 0. So somehow the lesson is that Stein fillable are nice, but if you go to the weakly fillable word, then you have to do a little bit more sophisticated algebraic topology. And so what is the next knot? So we know that -1 surgery is fine. It will always produce you tight structure. So what's the next knot after the unknot? So we studied +1 surgery on the unknot. What's the trefoil, right? So the next time we will deal with the trefoil, and we do +1 surgery on it. And in fact, we already proved, sort of between the lines, that this is not 0. So this is also a tight contact structure. And I would like to get back to the discussion of this tight contact structure in some extent next time. But if you feel that you would like to waste some time today evening, then you can just try to prove it. All the ingredients are there. Actually, the proof is in your notes. It's just, the letters are there, so you just have to put them in the right order. Okay, thank you. So, before finishing, I have to change personality. And now I will become an organizer. And I would like to make one announcement. Namely, there will be a party upstairs on the second floor.